In the previous video, we saw how statistics is the core element of machine learning. In this video, we'll delve into the elements that accompany statistics, acting like suitcases carried along the journey. Linear algebra, computation theory, cognitive psychology, and optimization. Let's explore what each of these elements contributes and why they are important. Linear algebra includes matrix theory and operations on vectors and matrices, and it's essential for working with data in various forms. And how does linear algebra apply in machine learning? Linear algebra is crucial for data representation. Additionally, deep learning involves advanced mathematical concepts related to linear algebra, which are necessary for understanding deep learning architectures like convolutional and recurrent neural networks. When we talk about computation theory, we refer to solving problems using algorithms. How is this related to machine learning? The theory of computation provides tools to understand the complexity of algorithms and the computational power required to solve specific problems. Additionally, learning and optimization require computational power, which translates to time and money. Therefore, it is important to measure and evaluate these aspects effectively. This may not be crucial when working with a decision tree using a moving average and the RSI of Amazon's daily historical data, but it becomes fundamental when evaluating a deep learning algorithm, such as a long short-term memory network for predicting stock price movements based on high-frequency trading data. This type of model can be computationally expensive due to the vast amount of data and the complexity of the calculations involved. You might be surprised to see that one of the suitcases is cognitive psychology. Cognitive psychology refers to the study of how humans process information, make decisions, and solve problems. Why should we care about this when we are talking about the ultimate involvement of machines? First, to mimic the way humans make decisions. The decision tree is an excellent example of an algorithm that mimics human thinking. A decision tree splits data into subsets based on the answers to sequential questions, much like how humans would logically break down a problem into smaller, more manageable parts. Additionally, a model that mimics human thought processes can be designed to be more interpretable. For example, with visualization techniques, in the image, you can see a snapshot of the TensorFlow visualization tool. This tool allows users to interactively see how neural networks process data, understand the weight and significance of different neurons, and observe the impact of various features on the final output. This visualization helps in understanding and debugging complex models, making the machine learning process more transparent and comprehensible. Optimization. In the context of machine learning, optimization refers to the process of adjusting a model's parameters to minimize a loss function. In other words, it's about making the model perform better. Let's consider the two images to understand this concept better. In the first image, we see small steps being taken along a loss function landscape. Small steps can sometimes leave you stuck in a local valley that isn't the optimal solution. This is because the steps are not large enough to escape these local minima. In contrast, the second image shows what happens when larger steps are taken. While larger steps can help jump over small valleys and avoid getting stuck in local minima, they also risk overshooting the optimal solution or landing in a different suboptimal valley. Balancing the step size, known as the learning rate, is crucial in the optimization process. The learning rate determines how big each step should be when the algorithm updates the model's parameters. Too small a learning rate might result in getting stuck in non-optimal solutions, whereas too large a learning rate might skip over the optimal solution altogether. In the next video, we will see the machine learning pipeline. This pipeline involves several key steps: defining the problem, collecting and pre-processing data, selecting and tuning algorithms, training the model, and finally, deploying it for predictions. This process ensures that the model is accurate and effective for real-world applications.